Hey there everyone. Today in this video I want to talk about the most important, the captain of all the probability distributions of continuous random variables, which is the normal distribution. And the normal distribution, I've got a few of them here. It's not a single distribution, but it's a family of distributions. And each one of these things is described completely by a mean and a standard deviation. And sometimes people write it like this. And you'll notice that we're using these Greek letters that tells us that we're talking about kind of a idealized population-like scenario. Not so mu is not the sample mean of a sample, right? This is the true mean of some population. Over here we've got a few examples of some different probability distributions that are normal, and we have the descriptors for them here. So like mu equal to 0 means the mean is 0, is the way we read that, and the mean is this place right here at the peak of these curves. The other thing that we need to describe this is sigma, right? The lowercase Greek letter sigma stands for standard deviation. In this graph, they've provided us with sigma squared, which is the variance. But all we need to do is take the square root of that in order to get the standard deviation. And I would kind of feel like the reason we care about standard deviation is because of the normal distribution. So let me show you how the standard deviation plays an important role in describing a normal distribution. So let's take a look at this blank curve right here, and we're going to draw on it. I think I'll make it a little bit bigger. Oh, and so while I'm doing that, let me just point out that all of these normal distributions, there's a whole family of distributions that are described by a mean and a standard deviation. They all kind of have the same shape, but of course they're not exactly the same. But they're all they're the same shape, they're just like stretched out and squished, right? And they can move around on the axis too, right? That's like what we saw here. Some are kind of stretched out. Those are the ones with larger standard deviation, as we'll see, and then some are kind of squished. Okay, so let's look at a particular one. All right, so this is an unlabeled normal distribution, and I'm going to make it into a labeled one. Let's say this is a normal distribution with mean 6 and sigma, our standard deviation, is going to be 2. All right, so the mean is 6 means that the peak of the bell occurs at 6. And then here is how the standard deviation works. So I'm going to just maybe switch over to a different color here. So right, when you're walking up, say walking up a hill, like when you're walking up this hill, it gets steeper and steeper and steeper. But then after a while, you get to some point, like here, and instead of getting steeper and steeper, it starts to get shallower and shallower. So it's like at this part of the curve, it's getting steeper at every step. And once you get up to this part of the curve, it gets shallower. And then when you get to the top, it does the same thing again, right? It starts to get steeper and steeper, and then it gets shallower and shallower as you go down. So that place, that special place where it changes from getting steeper and steeper to getting shallower and shallower, occurs precisely one standard deviation away from the mean. And same on the other side, because the normal distribution is a symmetric distribution. We know that it's going to be the same on both sides. So that means that if I want to mark off this tick mark and know what it is, I know that it's one standard deviation more than the mean. So that's the standard deviation, our sigma is 2, and our mean is 6. And so that means this has got to be an 8. And if I'm going one standard deviation to the left, this is 4. And then I can go another one and another one. And here's 10 and 12 and so on. And it's important to know that this curve, although it looks like it's getting close to, it looks like it is 0 by the time you get to 12, right? It's not. This curve, this theoretical mathematical object, never gets to 0. It goes on forever and ever. Okay, so that is how sigma shows up in this picture of the normal curve, and that's why, it suffices to just know these two numbers in order to describe this normal distribution, right? You just need to know where it is situated along the number line. And then you need to know how fat it is, right? Is it stretched out or is it skinny? This is, being considered to be a probability distribution. And that means we know what the area is, right? The area has to be 1. And if the area is equal to 1 and we know the shape of the curve, then we'd be able to, in principle, figure out the height of the curve. That's why the ones that have smaller standard deviation up here, right, they're taller because the area underneath these curves has to be equal to 1. And the ones that are fatter are shorter because they have to have the same area. Okay, so anyway, let's come back here and learn about how to compute some of these areas. Because this isn't like the uniform distribution, right? The uniform distribution was shaped like a rectangle. We're looking at intervals of that rectangle. It's pretty easy to compute the area of a rectangle. So that was fine. This is not a geometric object that you learned how to find the area of when you were, taking geometry. But there is a way of actually computing it exactly, but that involves calculus, and that is beyond the scope of this particular course. So we have a couple of rules, and then there's a table that's going to tell us how to compute some of these things. And also, Excel will do it for you. Excel will do everything for the normal distribution for you. All right, so there's a rule called, sometimes, I think our textbook calls it the empirical rule, but I call it the more helpful name, I think, of the 68, 95, 99.7 rule. And this rule has 3 parts. The first part says that if you have a normal probability distribution, then there's a 68% chance your random variable is going to land within 1 standard deviation of the mean. Let me write that down. Okay, so I've written this with a little bit of math notation, so we should just watch ourselves here, make sure that we've got this. This is mu minus sigma, so that's, in this case, for our example, it's 6 minus 2, comma mu plus sigma, so that's 6 plus 2. And if I write that down again, this is 4 comma 8. And I've used this interval notation. When you put these square brackets around and have a comma in the middle, that's just talking about that part, the number line that's between 4 and 8. And the fact that there's a 68% chance of x being in that range tells me that the area of this region is 0.68. Now that's the first part of the rule. The second part is that there is a 95% chance that x is in, oh no, I've not left myself enough room. Let's come down here. Mu minus 2 sigma and mu plus 2 sigma. And that looks like this. So if I've got mu minus 2 sigma, that would be minus 4 here. So I'd have 6 minus 4, that's 2. And 6 plus 2 times sigma, which is 2 here. 6 plus 4 is 10. All right, that's within 2 standard deviations of the mean. So that means this area is 0.95. And the last part of the rule is the 99.7 part. And it says that there is a 99.7% chance that this random variable will take on a value within 3 standard deviations of that mean. So that means this interval, let's see, we're going to have mu minus 3 sigma up to mu plus 3 sigma. And that's going to give us, let's see, 6 minus 6 is 0 and 6 plus 6 is 12. So that's going to give us this whole region from 0 up to 12. And our rule is telling us that there is, this random variable, whatever it is, has a 99.7 chance of being found between 0 and 12. Now you'll note that 99.7 is not 100, right? So there is a tiny bit of probability / area that is left over and sits outside of these numbers. So out on these tails, right? The upper tail and the lower tail is what we call these. And though that area is very, very tiny, but it's not 0. And no matter how high up you cut this off, there will always be a teeny tiny bit of area going off to the right. These tails are infinite. Okay, so that's the 68, 95, 99.7 rule, which is probably the handiest thing to know about the normal distribution. Calculating other areas in the normal distribution requires some fancy math or some kind of lookup table or Excel. And in the next video, I'll show you how to do some of that stuff in Excel.